Dear guests, teachers and students, welcome to the Faculty of Science public lecture entitled Reading Your Mind, Mathemagics. I'm Zhang Yuan, the head of the Math Department of Hong Kong U. So, kids start learning math the moment they start exploring the world. They use their fingers to count. Remarkably, brain researchers know that we see a representation of our fingers in our brain, even when we do not use fingers in calculation. Due to the fact that we have 10 fingers, the decimal system is widespread. We use the decimal system every day while dealing with money, weight, length, etc. So are there any other number systems besides the decimal system? In this talk, we will look into this question from a magic game. The magician gives you a set of mind reading cards, several cards printed with different numbers. And you pick up a number of your choice, and then the magician can read the number in your mind in no time. How can this be done? Some underlying magical tricks or some underlying mathematics? Dr. Doris Zhang will explain and share the trick with you shortly. Dr. Doris Zhang is an assistant lecturer in the Department of Mathematics at Hong Kong U. She got her PhD degree in applied mathematics at the City University of Hong Kong in 2009. Her research interests are asymptotic analysis, special functions, integral equations, and ordinary differential equations. Dr. Zhang commits to teaching and nurturing the next generations mathematicians, and her teaching areas include University Math 1, multivariable calculus, and linear algebra. Without further ado, I now pass the floor to Dr. Zhang. Please.
Thank you, Professor Yuan. Good afternoon, everyone. Welcome to the talk. So let's start talk from a puzzle. So one student asked me one question at the beginning of the semester, and which inspired me to give this talk. The question is like this. So I have 100 bottles, and 99 of them include pure water, and only one bottle of poison. And I would like to find out this bottle. Of course, the 100 bottles, they are totally the same. And I would like to use mice to test this liquid and try to find out which of the bottle is poisonous one. And of course, it's not very good to use the animals to test it, but we just assume that we will use mice to do the experiments. And here are some assumptions. The first assumption is that if a mouse drinks the poison, even just a little, it will die in 1 week. It will not die immediately. If it will die immediately, then I can use only one mouse to test the liquid, right? One by one. So it will die in 1 week. And the second assumption is that one mouse can drink more than one bottle of liquid. And the third assumption is that one bottle of liquid can be drunk by more than one mouse. So the question is that in order to find out the poison in 1 week, not immediately, in 1 week, how many mice do I need at least? So do you think how many mice do I need at least? For example, now if I have only, let's say, 2 bottles, so 1 mice is enough, right? If I have 2 bottles, then how about if I have 3 bottles? Let's say 1, 2, 3. How many mice do I need? 2, right? I can use one to drink the first bottle and the second one to drink the second bottle. And how about if I have 4 bottles? Do you think how many mice do I have? Do I need to have at least 3? How many mice? So here I think 2 is enough, right? For example, I can let the first mouse drink bottle 1 and bottle 2, and let the second mouse drink bottle 2 and bottle 3. Why? Because you can see if only the first mouse die, which one is the poisonous one? The number 1 bottle, right? And how about if both of them die? Then that will be number 2, right? And if only the second one die, then number 3 will be the poisonous one. And if both of them are alive, then the fourth one. So here you can see if I have 4 bottles, then I only need 2 mice. How about 100 bottles? How many mice do I need? Do you have any ideas? Okay, before we start to explore this question, let's look at a game. Let's play a game first. So would you please pick your lucky day of the month? Let me ask one. So how about the little boy over there? So would you please pick your lucky day and do not tell me which one is your lucky day. And I will ask you several questions. You just tell me yes or no. Alright? Okay, pick one day. Your lucky day? Okay? Okay, let's see. Is your lucky day on this card? Yes, okay, so his lucky day is on this card. Is your lucky day on this card? Yes? Okay. How about this one? Is your lucky day on this card? Yes, okay. Yes. How about this one? No, his lucky day is not on this card. And how about this one? No. Okay, so let's repeat. His lucky day is on this card, and this card. But it's not on these 2 cards. So, I guess your lucky day is a Monday, right? In November, it's a Monday, right? Is it November the 7th, right? So cute. Yes. So then I think it's easy for you to understand that 7 is only on these 3 cards. But the question is, how can we arrange these cards? So how to pick up the number on these cards? Why I put, these are all the odd numbers, why I put the odd numbers here and why I put these numbers here? How to choose the numbers? Okay, in order to explain this, we should look at the binary system first. Binary system was a system which was invented at the end of the 17th century by Leibniz. And it is a method of mathematical expression which uses only 2 symbols. So typically 0 and 1. So in binary system, we do not have 2, we do not have 3, 4, 5, 6, 7, 8, and 9. Only 0 and 1. And you may know that we use the binary systems in our computers, right? And because it is easily understood by machines, there's only 2 states of the binary system, on and off. Or you can say 1 and 0. But how it works, how to write the binary numbers? In order to write the binary numbers, let's look at the decimal system first. So we write the natural numbers. So we start from 0, 0, 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And you will find that we run out of the symbols. So can we introduce more symbols here? Some students say, yes, we can introduce more symbols, but can you imagine that we have to remember infinite symbols to represent infinite numbers? That's ridiculous, right? So we have a very clever way to represent the numbers, which is called positional system, right? So after we run out of all the symbols, we can add a 1 in front of it. So there will be 1, 0. And because we have 10 symbols here, so this one is 10 times this is the 1's position, and this is the 10's position, which is 10 times 1's position. And for binary system, we can also write the numbers like this. So we start from 0, and then 1. And then we run out of all the symbols because we can only use 0 and 1. And what we can do, we add 1 in front of it. But this 1 is different from this one, right? So it's only because we have 2 symbols here. So this will be 2 times this position. So if I say this position is 2 to the power 0, which means 1's position, then the second one will be 2 to the power 1, right? And then the next one will be 1, 1, and then I run out of the symbols, so the next one will be 1, 0, 0. And this one means 2 square, right? So this one means 2 square. So it's almost the same as the decimal systems. So you can see this is the binary system. And the question is how to convert a binary number to decimal number. I think from this example, it's easy for you to understand. Because the first position is 2 to the power 0, and the second one is 2 to the power 1, and 2 to the power 2, and so on. So if I give you a binary number, which is 1, 1, 1, 1, 1, 1, 1, 1, you just have to add them up, right? Just to do some production and just add them up. So you will get it's 128 plus 64 plus 32 plus 16 plus 4 plus 8 plus 4 plus 2 plus 1. So this is 255. And how about if there are some zeros inside it? No problem, you just skip that position. So we can see this is 128 plus 16 plus 2 squared, which is 4 plus 1. So this number is 149. So if I have a binary number, then I can convert it to decimal number. How about if I have a decimal number, how to convert it to binary numbers? For example, 100. How to write it in binary system? So we have 2 ways to write it. The first way is that you can use 100 to divide by 2. So let's look at it. So first you may divide it by 2 and you get 50 and the remainder is 0, right? And then we use 50 to divide by 2, you will get 25 and the remainder is 0. And then 25 divided by 2 is 12 with the remainder 1. And then 12 over 2 is 6, the remainder is 0. 6 over 2 is 3 and the remainder is 0. And 3 divided by 2, the quotient is 1 and the remainder is 1. So if I change it to decimal, I change it to binary numbers, so it will be 1, 1, 0, 0, 1, 0, 0. And because this is a base 2 system, the binary system is with base 2, right? Actually, you can use this method to change it to any base. For example, let's say if I want to change 100 to octal system. Octal system means that base is 8. Then how to do it? I can use the similar method to do it, right? I use 100 to divide by, so let's try, let's use 100 divided by 8, so which is 12 with remainder 4. And then I divide it by 8, which equals to 1, the remainder is 4. So 144. So you can say that 100 equals to 144 with base 8. So we may use the similar method to convert to any base. And the other way is that you may also try to write 100 by the power of 2's. So the power of 2's, for example, 64, this is 2 to the power 6, right? So we may write it by 64 plus, and then you can think about what else I can use. 32. 32 is 2 to the power 5. And then that is 96 already, so I add a 4 here. 4 is 2 squared. So that means this position is 2 to the power 0, 1, 2. So this will be 1 because I have 2 squared here. And then I do not have 2 to the power 3. I do not have 2 to the power 4. So this position will be 0. And then 2 to the power 5, 2 to the power 6, because I have 2 to the power 5 and 2 to the power 6. So this will be 1 and 1. So this is another way for us to convert a decimal number to its binary form. And I think you may understand why we use decimal systems, right? Because we have, due to the fact that we have 10 fingers, so we use the decimal systems. And actually, I think in the history, a lot of countries they use the decimal system. For example, the Roman numbers. Actually, we still use Roman numbers now, right? We use I for 1, we use V for 5, we use X for 10, and then, so you know how to represent, right? 1, 1, be 2, I is 2, and then I is 3, IV is 4, and then V is 5, VI is 6, VII 7, VIII 8, right? And this is also a decimal system. And in the Egyptian mathematics number hieroglyphs, you can see this is also a decimal system. We use different graphs to represent different numbers. For example, here, you can see we use a flower to represent 1,000. We use a finger to represent 10,000. And we use a frog to represent 100,000. So you can see that this number is 3,244. And actually, this is also decimal systems, right? So it's close to our decimal systems. And do we have some other number systems? Yes, the Yuki language in California and the Pami language in Mexico have octal systems. The octal system, because I just checked from the website, they say that because the speakers count using their spaces between their fingers rather than the fingers themselves. Some students ask me, what is the merit of octal systems? I think maybe in the simple math, 8 is more easily divisible by 10. So maybe there's some advantage of this octal system. So that's why people there use octal system. And a long time ago, actually, every civilization had their own number system. So we've already introduced Roman, Egyptians, right? And the Babylonians used a sexagesimal system. Sexagesimal means the base is 60. And now we still use base 60, right, to count hours. 1 hour is 60 minutes. So we also use it now. And some countries, they use a base 20 systems. They count with their fingers and toes. And the others, they only count 1, 2, 3. And anything more than 4, they just say that many. And we can see that the Babylonians, they use the sexagesimal systems and they use these symbols to represent 1 to 59. And now, actually, do we have the similar systems? Yes, but we do not use these graphs because it's difficult for us to remember. So now, if we want to use a base more than 10, we will use letters to help us. For example, we may use all the capital letters, A to Z, plus 0 to 9, to represent a base 36 system. And we may also use all the capital letters and all the small letters to represent a base 62 system. Now my question is, why we have to use this system with large base? It's not convenient, right? Then why we have to use this? Have you seen any number use this to represent? Have you seen any numbers? Sometimes when you click the YouTube, you will see that youtube.com watch, and then, so what's this? Just like some code, some letters here, right? And actually, this is I'm not sure whether it's base 62. I think it's more than base 62 because sometimes you can see some special symbols inside it. So I think the base is more than 62. But why? They have to use a large base to represent it. Why not use decimal system to represent it? So because the reason is that we can use less digits. For example, A, B, C, D, what this means. If in a base 36 system, A, do you still remember we use 10 symbols and then A, right? So A means 10. And B means 11, right? And what is C? C means 12 and D means 13. Yes, D means 13, and then you add them up, you can find in the base 36 system, this can represent 481,000, more than 481,000. And only with 4 digits, we can represent a number which is larger than 1 million. So it's quite convenient for us to represent the large numbers. And let's look at this YouTube URL. You can see it contains 11 digits, 11 letters here, and actually 11 digits which can represent more than 5 times 10 to the power 19 different numbers. So it's quite convenient because YouTube videos, we have really too much YouTube videos, and if you want to use decimal places to represent it, that will be a very large number. So that's the reason we use a system with a large base. And I think the base is more than 62. Maybe it's 80 or something like that because it can include a lot of special symbols like the question mark or underline. So if you check the YouTube video, you can see a lot of special symbols there. So that means the base is larger than 62. And if you want to represent a number, it looks like very large. So you can use binary, right? So let's see the picture here, 10001. It looks quite a big number, but what number is this? It's a binary number. It's a number in binary system, so actually this is 17 only, right? Because you can see this one represents 1, and then this is 2's place, 4's place, 8's place, 16's place. So this number is 16 plus 1 is 17. So with a large base, we can represent a very large number in short digits. So I think that is the usage for large base. And in ancient China, we also have this binary system. And I will not explore too much to this, so you may explore this by yourself. You may check the videos or the website by yourself to look at what is I Ching diagram. So basically, the broken stick here means 0, and the whole stick here means 1. So this is number 0 to number 7. And this is H trigon. And now we know that we can use our fingers to represent numbers, right? Usually we will say, this is 3 and this is 4. But can we use our fingers to represent a binary number? We can. And it's easy. You can see that we can define this one to be 1, 2, 4, 8, 16. Right? And for example, if I want to represent 7, then this is 1 plus 2 plus 4. So this is 7. And if you do not have pencil or a paper, you may use your fingers to remember the numbers. So, and the question is, what is the biggest number we can represent by our 2 hands? What is the largest number we can represent by 2 hands? 1, 2, 4, 8, 16, and then 32, 64, 128, 256, 512. So in total, we can represent 1023. So that is a relatively big number, right? So next time, if you want to represent a number, you can use your fingers. If you do not have pen or pencil, you can use your fingers and use binary fingers to represent it. And now let's go back to our game. So how to pick the numbers on each card. First, I have to write all the numbers to its binary system, to its binary number. So for example, 1, then I can represent it by 1, right? And then 2, so this will be 0, 1. And for example, let's say 31, this will be 1 plus 1 plus 1 plus 2 plus 4 plus 8 plus 16. So this is 1, 1. So actually we should read from here. 1, 1, 1, 1, 1. This is 31, right? And another example, for example, 15 is 1, 1, 1, 1. And 13 is 1, 1, 0, 1, right? And then I choose all the numbers whose ones place is 1. So you can see the blue one here. I pick up all the numbers with whose ones place is 1 and put it on the first card. So that's why on the first card we can see only odd numbers, because their ones place is 1. And then I choose the twos place is 1. All the numbers whose twos place is 1, I pick it out and then put it on the second card. And then I choose all the numbers whose fourth place is 1. I pick it out and put it on the third card. And the 8th place is 1, we put it on this card. And the 16th place is 1, we put it on the last card. And for example, if 29, we can represent it by 16 plus 8 plus 4 plus 1, right? So you can see that it will be on the first card, third, fourth, and fifth card. So if you tell me that my lucky number is on the first card, third card, fourth card, and the fifth card, then I can calculate that your lucky number is 1 plus 2. I just have to look at the first number on this card. 1 plus 4 plus 8 plus 16. So that would be 29. And the little boy tells us that his lucky number is on the first card, the second card, and the third card. So we just have to add up the first number on these cards. So that is 1 plus 2 plus 4. So we get that his lucky number is 7. And let's look at what is my lucky number. My lucky number is not on this card. It's on the second card. So you may guess what is my lucky number. It's on this card. It's not on this card. It's not on this card. And it's on this card. So which day is my lucky number? Which day is my lucky number? It's on the fifth card and it's on the second card. Oh, yes. So thank you. Today is my lucky day because I can see you guys here. And I'm so glad that you can join my talk. Yes, thank you. So this gives us one idea how to use the binary system. And now we can go back to the first puzzle. Now do you have any ideas? How many miles do I have, at least, to test these 100 bottles? It's very similar to the game we played just now. So what we have to know is that, and Actually, we've already changed 100 to its binary, right? Do you still remember that if you 100, then the binary number is 1100,100. And do you know how many mice do I need at least? 7, right? So because the largest number contains 7 digits, so that I need 7 mice. So the first thing I have to do is I have to convert all the numbers to their binary numbers, and then I write out all the numbers, and then I choose the first mouse, and give it all the ones place is 1, right? Give it all the bottles whose ones place is 1, and the second mouse whose the twos place is 1. Let it drink all the bottles whose twos place is 1, and then the third one, I let it drink all the bottles with the fourth place is 1. And then the next mouse, the 8th place is 1, the 16th place is 1, the 32th place is 1, and the 64th place is 1. And so you can see each mouse represents a position, right? And how about if these 3 mice die? What is the number of the bottle? What is the number of the bottle? So the number of the bottle should be 37, right? Because you can see that if this mouse died, that means 32. And this mouse represents 4, and this mouse represents 1. So in total, the number is 37. So you can see that we only need 7 mice. So that's a very interesting question. And so now I have one question. If there are 2022 bottles in total, then how many mice do I need? Two to the power 10 is 1024. 2 to the power 11 is 2048. So how many mice do I need? 10. So if you say 10, actually, you forget 2 to the power 0. Because, let's try to look at this question. So, if I write 2022 in its binary number, so this will be a 11 digits number, right? This will be 11, so because 2 to the power 11 is larger than this number, but 2 to the power 10 is less than it. Or we may try to write it out. This will be with remainder 0, and then 505 with remainder 1, with remainder 1, with 0, with remainder 0, and then divide by 2. So we can repeat the process to see what will be the binary number. What is the binary number? It should be 1, 1, 1, 1, 1, 1, 6 ones, and then 0, 0, 1, 1, 0. So how many mice do I need? 11, right? Because this means 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 4, and so on. 2 to the power 3, sorry. 4, 5, 6, 7, 8, 9, 10. And so here I need 11 mice. From 0 to 10, I need 11 mice. And the next question is, how many bottles can I test at most if I have n mice? For example, if I have 2 mice, then I can test 4 bottles, right? At the very beginning, we've already proved it. And how about if I have n mice? Yes, I can test 2 to the power n different bottles, right? Actually, the last bottle, we no need to test it, right? Because if all the mice are alive, then the last one will be the poisonous one. So this is about the game. And the last game I want to share with you is called Neem. So this is a very interesting game. Let's look at how to play it. Neem is a mathematical game of strategy in which 2 players take turns to removing the objects from distinct heaps or piles. And the number of coins of heaps is up to you. So you can have 3 heaps, and each one, for example, have the first one have 3, the second one have 4, the second one have 4. So it's totally up to you. So let's say, for example, the first one we may have, the first pile we have 3 coins, and the second one we have 4 coins. And then we have 5 coins. It's totally up to you. And how to play the game? On each turn, a player must remove at least 1 object. So you cannot say that I pass this turn. No, you must remove at least 1 object. And you may remove any number of objects, but they must from the same pile. They must from the same pile. So for example, you can see I want to remove 3 of the last one. Then it's okay. You may remove the 3 from the last pile. It's okay. So this is the requirement of the game. And the winner, you may define what will be the winner, but today we define that the winner is the player who makes the last move. That means who takes the last coin will be the winner. But you may define by yourself that who takes the last coin will be the loser. It's up to you. And here, I show you one game. Let's look at the game here. So 2 players are playing this game. And the first step, so here we have 3 piles, right? 3, and then 4, and then 5. And then the first one, A takes 2 from the first one, right? And then the second step, B takes 3 from the, A takes 2 from the first one, and B takes 3 from the third pile. And then A takes 1 from the second pile, and so on. You can see that the last step, A takes the coin and wins. So B have no choice to here, right? He must take 1, and so A wins the game. So A wins the game. So now our question is there any strategy to play this game? So how to play the game and you can win the game? Naturally, this is also a binary problem. Let's look at it. So in order to explain this one, so we have to introduce another kind of sum. It's not the same as sum notation. We call it Neem sum. For example, in order to calculate the Neem sum, I have to write each number to its binary form. For example, 2 plus 3. So I have to write 2 to 1, 0. And I have to write 3 to 1, 1. And then I compare each position. If they are equal to each other, for example, it is 0, 0, or 1, 1, then the Neem sum of this position will be 0. So we calculate position by position. And here you can see 0 plus 1, because they are different digits, so we write down 1. If they are the same, then we write down 0. So you can see this equals to 0, 1. and this is 1. And for example, 5, we calculate the mean sum of 5 and 3. 5 is 1, 0, 1. And 3 is 0, 1, 1. And you can see that the first position, 1 and 1, so that will be 0 because they are the same. So we will write down 0. And then 0, 1. See, 1, 0, so we write down 1, 1 here. Can you understand how to calculate this one? If with the same number, then we write down 0. If they're different, the same position with different numbers, then we write down 1. Okay, so 7 plus 4, you can see 1, 1, 1 plus 1, 0, 0. So only the first position are the same, so the answer is 0, 1, 1, which is 3. And it's not difficult to prove the mean sum satisfies the associative law and the commutative law. So when you calculate the mean sum, if you want to add 3 numbers, you can add the first 2 numbers and then add the last one, or you may add the last 2 numbers first. The result will be the same. And if you want to calculate A plus B, you may calculate B plus A. It's totally the same. Now let's try to do what is the mean sum of 1 plus 3 plus 5 plus 7. You may calculate any 2 numbers first because it satisfies the associative law. Or the other way is some students may write down all the numbers out and then compare each position. So what is the mean sum of this one? If you do not have pen or pencil, you may count by your finger. Right? For example, 1 and 3 is 1 and 2, right? So you can see the first position are the same and the second one is not, right? You may count by your finger if you do not have pencil or pen. Actually, the mean sum is 0, right? Right, let's look at it. If I add 1, 3, 5, 7, so I write all the numbers to its binary numbers. And then let's look at the first position. 1 plus 1 will be 0, right? 0, and this 1 plus 1 will be 0. 0 plus 0 will be 0, right? So the first position will be 0, and then the second position, 0, 1, 0, 1. We may add 0, 0 first, and then 1, 1, right? So the second position will also be 0. And how about the fourth position? 0. So this is 2's position, right? This is fourth position, 0, 0, 1, 1. So 0, 0 is 0, 1, 1 is 0, right? 1 plus 1 is 0. If we use mean sum, so the sum of this one will be 0. And how to play this game? Is there any win strategy? So first we have to write the size of the heaps as binary numbers. We write down the numbers and then we use mean sum to add these numbers up. And in order to play this game, we have to know 2 facts. I will not prove it. It's not difficult to prove these 2 facts, but you may play with it and you can see the fact. The fact is what? The first one is that suppose it's your turn. And the mean sum of the number of coins in the heaps is equal to 0. For example, if it's 1, 3, 5, 7, the mean sum is 0. Then whatever you do, the mean sum of the number of the coins after you move will not be equal to 0. For example, 1, 3, 5, 7, then you may remove any coins from any pile, but the mean sum will not be 0. You may play with it. And the second factor is that suppose the mean sum, it's your turn now, and the mean sum of the number of coins in the heaps is not equal to 0. Then there is a move. So you can think about the move, which ensures that the mean sum of the number of the coins in the heaps after your move will be 0. Then the question is, in order to win the game, suppose now from the very beginning the mean sum is not 0. And So you think the first one will win or the second one will win? So suppose we have two players, and if at the very beginning the Neem sum is not 0, so you should choose to be the first player, because after you move, the Neem sum can be 0. You should make sure that each time after you move, the Neem sum is 0, right? Because who wins the game, the Neem sum at last will be 0. So we should make sure that each time after you move, the Neem sum must be 0. Then you can win the game. So this is the strategy. Suppose that player A goes first. If the Neem sum of the number of coins in the heaps is not equal to 0, if it's equals to 0, then you have to choose to play the second one, right? You cannot play the first one, maybe we'll lose the game. So player A has the strategy to win. Always make a move that reduces the next Neem sum to 0. So let's look at, so for example, I have 3, 4, and 5 coins here. And what I can do to move it and to reduce the Neem sum to 0. For example, I can add, you can see that 3 plus 4 plus 5, this is not 0. It's 0, 1, 0, right? So for example, we may add 4 and 5 first. If we add 4 and 5 first, the Neem sum is 0, 0, 1. 0, 0, 1, this is 1, right? So I have to remove some coins from the first pile and let it be 1. So the Neem sum of 1 and 1 will be 0, right? So I have to remove 2 coins from the first pile. And then the Neem sum will be 0 now. If 1 plus 4 plus 5, the Neem sum is 0 now. So with this strategy, you can win the game. So you can see that here A removes 2 coins from the first one, and you can verify that each time after A removes the coins, the Neem sum is 0. So you may play the game with your friends after the talk. So much for today for the sharing. Do you have any questions? We may discuss it. Or if you want to play the Neem game with your friends, so we may discuss it. Do you have anything you want to share with me?
I have that game you're describing
Yes.
features in a very famous film
Yes.
called Last Year in Marienbad.
Oh.
L'année dernière in Marienbad. It's a French film
Oh.
in the 1960s.
Oh.
And they play it with matchsticks.
Is there an English version?
Actually on YouTube, and I don't know the
language?
I don't know the binary number for the YouTube. You can find Last Year. In English, it's called Last Year in Marienbad, or in French, L'année dernière en Marienbad.
Okay.
It's a French film.
Oh, I think I will watch it. Yeah.
And well, I don't recommend you to watch it because people can't understand what the film was about anyway. But that game,
Okay, thank you. Thanks for the sharing.
that game features in that played with matchsticks. So when I was at university, it was very popular to play the matchstick game. We didn't know what it was called. And the way we played it was the loser is the one who takes
the last one. Okay. Okay, yeah. So I checked on some online Neem games, and in some website, the one who take the last one will be the loser. Yeah. It also by matches, not the coin. Use matches to play it. Yeah. So thank you for sharing with us. So do you have any other questions or other comments? Yes, any? Okay, so can you understand it? Totally the binary system? Yes, right. Okay, so then you can play the game with your friends. And of course, you should design at the very beginning, the Neem sum must be non-zero. And then you go first, and then you can win it. Okay, thank you very much.